Well, good day, everyone, and welcome to another interesting session for this seventh lecture workshop on transdisciplinary areas of research and teaching by Shanti Bhatnagar Awardees. And today we have with us Professor Kalyanmoy Deb, who's a Shanti Bhatnagar Awardee in Engineering Science, the year 2005. And currently, he is University Distinguished Professor at Koenig, Endowed Chair Professor at Department of Electrical and Computer Engineering. Is also Professor of Computer Science and Engineering and Mechanical Engineering at Michigan State University, US. And he'll be talking to us today on a topic Evolutionary Multi-Criterion Optimization, an emerging computational problem-solving tool. He's a well-known figure in the area of computer science, but as a customary, I would like to introduce him to all the attendees. Like I've said that he is from Michigan State University, and his research interests are in evolutionary optimization and their application in multi-criterion optimization, modeling, and machine learning. He is and has been a visiting professor at various universities across the world, including University of Scotland in Sweden, Aalto University in Finland, Nanyang Technological University in Singapore, and IITs in India. He was awarded IEEE Evolutionary Computation Pioneer Award for his sustained work in multi-objective optimization, Infosys Prize, Third World Academy of Science Prize in Engineering Science, and the Memorandum Prizes, Distinguished Alumni Award from IIT Kharagpur, Edgeworth Pareto Award, Bhatnagar Prize in Engineering Sciences, and Bessel Research Award from Germany. He is a fellow of ACM, IEEE, and ASME, and has published over 600 research papers with Google Scholar citation of almost 180,000 with an H-index of 129. And the other details, you can go to his website and you can have a look at all his contributions, all sort of spanning for more than 30 years, I suppose. Yeah. So with these words, I now invite Professor Deb to kindly share his screen to deliver his talk.
Thank you, Dr. Saxena. Let me share my screen here. Okay. Put that up. Okay, so you are able to see my screen, right?
Yes, I can see your screen.
Excellent. Okay, so let me see if I can get the pen out from here. Okay, great. So thank you for this opportunity, and thank you, Dr. Saxena, for organizing this event, because I think this is a very important event for young researchers to look at what some of us considered old have done in our career. And then they can also get motivated and do even beyond what we have done. So this is an area, evolutionary multi-criterion optimization. It may not be a household name, but it is becoming very, very important in practice, particularly in industry and societal applications. As you'll see soon, that there are lots of opportunities in this area to contribute. So it's very new and a lot of things are emerging. And I have been, while I was in IIT Kanpur, I have been one of the pioneers in this field. I've started with one of the first few algorithms way back in early 1990s. And then now it has become a huge field with lots of PhD students, jobs, and commercial softwares. So I'd like to give you an overall overview of what this is, how this can be used to solve problems. So I'm currently, as Dr. Saxena has mentioned, a University Distinguished Professor here at Michigan State. So just one slide on what is optimization. I'll start my lecture with that, and then quickly go into what is evolutionary optimization, because it sounds like, you know, we are using some concepts from evolution and how the evolution can motivate us to do optimization. So we'll talk about that. And then quickly move to multi-criterion optimization, where we'll be dealing with multiple criteria or multiple objectives for the optimization, which is the new part. There are some existing methods, but they are not very efficient because they try to solve the problem in an indirect manner. So I'm going to show you what one or two methods are, then move to the evolutionary way of solving these multi-criteria problems. And most of my talk will be concentrated on this, what is known as EMO methodologies. I'll briefly talk to also about at the end about the current research and applications that are going on in this field, coming from various areas, and then conclude. So I start with this very busy slide. Here, as you can see, the application of optimization. So optimization is a process where you have certain variables that you can change, and you have one or two or more objectives that you want to minimize or maximize to achieve your goal. And then there are certain constraints that say certain variable combinations are not allowed because they would not be okay for this particular application. So with that, majority of the work in optimization happens in design and manufacturing. So as you can see here, there are lots of parameters, the angle, the thickness, the material properties, so many things. Easily you can get about 100 to 500 different variables in a problem like this. What could be an objective? Could be what is the overall weight. Another objective could be, okay, is it okay for a side collision or a front end collision? So if there's a collision from the front, what is the deflection that the passenger is feeling in his chest and his various places, right? So there you can think of lots of different criteria. So that's where the multi-criteria comes in a design. But it is kind of surprising that for many, many years now, people have been concentrating on one particular criteria, keeping everything else as a constraint. So we will break that ice and we're going to say, no, now we can handle multiple criteria simultaneously. So that's the whole purpose of this talk. And then you have modeling problems where you have a system. Here is a blast furnace I'm showing it with manufactured steel. There are a lot of inputs that goes into it. And then ultimately you get steel. So so if I give you certain inputs, what is the quality of steel that I am expecting at the end? If I can make a model of the quality of steel as a function of input, from data or from some knowledge of the chemistry or science of the process, that is what is known as a modeling. Now, optimization is used to come up with the modeling in many different ways, using neural networks today or deep neural nets, or from using, as I said, the known science that goes into it. Then there are scientific experiments that you do. Sometimes these experiments are expensive to do. So you do few and then you decide, I want to do 2 or 3 more. So sort of like a design of experiments, you're thinking, where do I put the next experiment so that I get maximum information out of my problem? So again, optimization is used there. Placement of objects in a 2D printed circuit board comes under this problem of placement, or in general, these are combinatorial optimization problems, including traveling salesperson. And supply chain is another one where there are lots of vendors that are supplying parts, and all of them needs to be coordinated, had to come at the right time, at the right place, so that the overall product can be fabricated. So coordination of all of them requires a huge optimization problem. Optimal control is another thing. Here, the variables are a bit more complex. These are usually time-dependent or distance-dependent variables. So they are difficult to solve, but there are optimization methodologies that can be formulated from it. Prediction of markets, prediction of weather, all these are common problems people use in society. So you basically do is make model until certain point based on the past data, and you then extrapolate the model to say what is going to be in the future. So if your modeling is good and reliable and extendable, then you can get a lot of benefits out of this. Then with the data mining literature being there, all the data analytics and machine learning tasks, I'm kind of covering both of them here, they involve an optimization process eventually to come up with the best model. So their optimization is very widely used. There is some notion of intelligence that can be related to optimization, because if you think of optimization, there's a huge search space, but in that search space, you're searching for good solutions. Now, good with respect to the objective functions that you're defining, right? So if you define your objective function and constraints in a way that the solutions of that can become an intelligent solution, so that it can have its own ways of interpreting, own ways of coming up with new solutions, then optimization can be a vehicle to get to that. So you see that there are various kinds of problems that exist in the practice where optimization can be one single method that can be used to solve so many problems. So that's about the problem. How about the algorithms now? So there are, again, many algorithms that exist. They can be broadly classified into two classes. One is point-based, where we start with a point. A point means one particular solution in the n-dimensional space. These are your variable vector. And then with iteration, you improve the solution and hope to get to the maxima, for example, in this case. If you're a minima, you would have gone to that point. But then if you start from another point, you may have gone to another optimum. So if there are multiple optima like this, if this is the objective function landscape, then it depends on where you're starting. You will end up at a nearest or at a convenient point that comes from there. It depends on the algorithm where it will take you. But these kinds of method, because it's dealing one point in every iteration, they can be theoretized, and lots of theory exist, and they usually have a proof that starting from here for certain class of problems, you can get to the optima with some guarantee. Linear programming is one such algorithm as well. But the population-based methods are completely different to the point-based methods. There you start with a population of points, for example, these points maybe, and then the algorithm suggests another set of points. Maybe there are some overlap of some points, and this is how you move. Now, because you're dealing with a population, it's very unlikely that you will get stuck into a local optimum. So we see a lot of examples in nature, because nature is a population-based procedure, because every species are working with a number of individuals and population members. So you can see how very interesting and optimal designs the nature had come up with in time. All you have to do now, if you're following this, we need to speed up the process so we don't have to wait millions of years before we come up with something useful. So all these different algorithms are bound by this theorem. They are called no free lunch theorem. So in 1997, only recently, I would say, these two gentlemen had come up with this theorem. It says, if you have two algorithms, A1 and A2, A1 can be a point-based, A2 can be population-based, or A1 can be even a simple randomized algorithm. If you're interested in comparing these two methods and say which one is better in a class of, in all possible problems that I might get in the future, okay? So there are all possible optimization problems are put into this big set. Now I apply A1 to every member of this problem class, problem set, and get a performance measure and agglomerate and get one number called P1. So P1 says how A1 did on all problems. On the same computer, on the same number of time and evaluations, we do the same thing for A2. And let's say the performance is P2. These two gentlemen have proved P1 is always equal to P2. So that means if you're interested in solving any arbitrary problem, there exists no one algorithm better than the other. Okay, so if your algorithm is better in certain problems, know that there exist certain other problems where your algorithm is not going to be better. Okay, but this NFL theorem breaks down if you're saying, no, I'm not interested in all possible problems. I'm interested in only the car design, the car body design, okay, or maybe the VLSI design. So then you can have one algorithm that is better than the other. So that's what people have been doing since 1997. They always mention what problem they're trying to solve, and then they provide the algorithm. So there are some point-based methods, which is shown here. For example, this point goes to that point if you go along the negative of the gradient, because gradient increases the function value, negative of the gradient will decrease the function value the maximum way. So if you go along the negative of the gradient at every point, that's the best direction to go locally around that point, but you go and find the best point along that direction, then you stop. And then at that point, you compute the gradient again and go along the negative direction, and you can come very close to an optimum of certain problems. There are other point-based and with few points, there are some algorithms as well, but most of these methods are either derivative-based or it uses direct search method that uses very simple principles. Population-based methods are quite different. They, as I mentioned, they start with a set of points. Here is a sketch of an algorithm. So you initialize a set of points, often at random in the entire search space, evaluate them so you know which is good and which is not so good. And then you go into a loop. So if you're not terminating, there should be some termination criteria of when you should terminate. Then you select the good solutions of PT. So let's say these are my good solutions out of the 7 solutions. So that's my what is known as a mating pool, P-T. Then you use that mating pool and apply several operators called recombination and mutation. They mimic the natural genetics kind of idea. If you consider binary coded strings, that means a set of binary bits are used to code a real number. Then you have a representation of 8 in this way, 10 that way. So if I have two solutions like this, you can apply a crossover where the right side of the cross site is swapped between the two. So this gets attached to that, and you get a new solution here. And that one gets attached to this one, and you get a new solution here. And that might produce something better, or it may not. So that's the recombination operator you apply. Instead of 1 point, you can have 2 point, and there are many, many ways to do that, about 50 different ideas that exist in the literature. Mutation is different from recombination, where you just use one of the population member and change its bits to its complement. It may result in an improvement or may not, but you still do it. But so recombination is a property with more than two or more parents are combined together to create one or more children. Mutation only takes one parent and it changes locally in order to get a new child. So you get a children population. So this PT is called the parent population, and P double dash is called the offspring population or child population. You evaluate, this could be the child population, you evaluate them, then you combine both these populations, and then you decide who is going to survive. So maybe 2 of these from the parent survives, and then some of these new solutions survive, and then you have the new population go back and do the same thing. When this works properly, you can observe that a representative point of the population moves towards the optima with a reduction in the variance, because you started with a really uniform distribution of population all over the search space. So you expect to have a large variance. And then as you move towards the optima, your variance is going to reduce. So it's kind of a cloud moving with the cloud getting denser and denser. Okay, so these kinds of things are not only just we are talking about, they've been applied to real world problems, like this Koenig elevator has been there since 1995. So which car would come to which floor when people are at different floors and pressing a button is done using this genetic algorithm. So I have picked this up from their manual, Allocate Landing Calls by Genetic Algorithms, which is one of the very early evolutionary algorithms. And it's been there since 1995. This is Japan Shinkansen, the bullet train, starting around 2006. All the latest versions, they are using genetic algorithms. Then the design of the nose is done using genetic algorithms. There are other designs and lots of applications that exist in the industry today. So if you think of where are these algorithms good at, first of all, they're very, very flexible. So you can come and change one part of the algorithm. They're so modular that it is only going to change that aspect. So if you're changing a crossover, you are basically saying how I should create new solutions. It doesn't change the selection process or the final survival selection process. So like that, they've been modular, and you can come and change the order of how you apply them or introduce a new operator. So they're very easy to be changed. Because we are dealing with the population, there is a better chance of finding the global optima that I mentioned already. But there is another benefit with the population, that you can find and store multiple solutions. So if your goal is not to get one solution, but a number of alternate solutions, these algorithms allow a platform for you to find that. And there is another important thing that needs a bit more time for me to describe, but it's called implicit parallelism. Because of the population, there is a parallel search that goes on that the point-based methods don't have. Okay, these are direct search methods, so we don't need any gradient or any other information. You can add procedural objectives and constraints, like if the power produced is so much, in order to store it, I need one more way to store it. So that kind of if then else, so that will increase the cost and everything, but my objective function and constraints can then be defined with if then else statements or any other procedure. It can be even a black box optimization that you could do, where you really don't know how the objective functions are. You don't see the mathematical structure of it. So usually the current myths and facts are that the point-based methods are fast because of just one point being moving to another point, but they have a local perspective. They're usually theory-based. They are successful in deterministic problem where there is not much uncertainty or dynamism in the problem. They're hard to modify because somebody told you what to do. So if you're looking for an algorithm that needs to be customized for a problem, these methods are not very good. On the other hand, population-based methods are known to be slow, are global, but they have a global perspective. They can be used with parallel hardware as well, very flexible. They're great potential to be applied and easy to customize. So some of these facilities here, advantages here, are making them very, very popular. And remember the NFL theorem, that suggests that you cannot have a single algorithm to solve all kinds of problems, which means that for a problem class, like for example, the car design or the gearbox design, there can be one algorithm. So that means we need a customized algorithm that can be developed for a particular class of problem. So we then started to concentrate on customization of algorithms. So here is a problem I got from PTC Industries. It's a real problem. You melt a certain amount of metal, you pour them to make some casting. So you do not one time, you do many, many times. So if you pour some of these and some metal is left, and none of this can take that much, so that becomes a waste, right? So you come back and melt again after 3 hours and you do that. So now you decide when you melt certain amount of metal, which of these casting you're going to do so that minimum amount stays there, not in one go, but in many times you do this. So that's a typical problem that came from the industry. When I looked at their time horizon for which they want to optimize the system, it requires about 50,000 variables, 50 to 100,000 sometimes. Okay, so when you formulate, this is the formulation you get, but to make it very simple, Xij are the variables, which is a matrix, which is shown here. So if you have 10 orders, 10 different castings you have to make, and each casting had different demand. So first one, you need to make 7 copies. Second one, you need to make 7 copies, and so on and so forth. This is my first heat. So this is my solution. First heat says, okay, melt with the melted metal, which is about 650 kilo in this particular case. Let's make 1 copy of the second casting, 1 copy of the third casting, 2 copies of the 7th casting, and 1 copy of the 8th casting. And you will be utilizing 623 out of 650. So your metal utilization is 95.85%, the ratio. Now you go to the second one, it has another way to do things, and you have 94.62%. So like that, you do and finish and get your demand made, and then you see what is the average of these. So all these are formulated here. So Xij is this matrix. This is what my optimization algorithm should find. So with respect to that, my objective function is linear, as you see, linear to the Xij. My constraints, because the 623 has to be less than equal to 650, you cannot utilize more metal than what you melted. So this is a must constraint. It's also linear. And then this sum has to be exactly equal to the demand. So that constant also have to be met because you don't want to make 1 more copy or 1 less copy. So all are linear. So you can use a linear programming, and linear programming methods you can solve like thousands of variables, not a problem. So what was the issue here? This problem. Xij, each of these numbers have to be an integer. Imagine this being 1.5. That means that second one, you are going to make 1 copy now and come back later and do 0.5 copies. But in casting, it's not allowed, right? You have to either do 1 or 2 or 0. So this has to be integers. And that makes all the difference to existing algorithms. Linear programming now have to be integer linear programming. And then there is a method called branch and bound, or there's a sophisticated one called branch and cut, which basically assumes that the problem is a non-integer. It's real. So you can use a simplex method of linear programming. And then if you get a non-integer value, you have to branch using one of them and then keep branching. And there are ways to bound them. So this branching can really grow and can make things really exponential, although the original linear programming is not exponential. So when we take a very small size problem, like 310 variable problem, Simplex, which is a well-known software for solving these kinds of problems, can solve it in 0.05 seconds. So it's pretty good. And we get 99.256%, which can be proven to be the optimum for this case. Then we increase the variable to 1,000. Simplex can solve in 0.13 seconds with a very good metal utilization. But when you go to 2,000 variables, it cannot solve. We are waiting all the way up to 15 hours, and it's still not able to solve. What happens, you see, in 30 minutes time that I'm showing you here with that Simplex to a 2,000 variable problem, is this blue is the number of branches it has made. So by the time you are 30 minutes, it has opened up about 35 million branches. So you can see how wide this branching has already become. And the red shows how many of them are still yet to be bounded. So there are about 35,000 of them. So you think another half an hour may solve it, but we went all the way up to 15 hours. Both of them were growing. So that means the dimension 2000 is a bit too much for this problem to handle. And this aspect in the literature is called the curse of dimensionality in optimization. So we came up with a population-based algorithm. I'm not giving you the entire detail, but just to tell you that the recombination is so useful here is that if you have two parents like this, and I'm taking a very small example only with 4 heats, but I still kept the 10 different castings. So you remember my matrix, right? So this is the two matrix, the two parents that I was talking about. Now, how do I create a child from these two parents? So I'm going to change my original recombination with this new customized recombination for this problem. See the way I do this. I look at the first heat from both parents and see if I can say if any one of them is better. So this one utilizes 343 kilos of metal. This one utilizes 625, and I have a vessel of size 650. So this is really close to 650. So this is much better than that. So I take a copy and put into my child. Then I go to the next one, and I notice that this one requires 808 kilo. This one requires 667 kilo. Both are infeasible. Both are more than 650, but this is a bit closer to being feasible. So I take that and put it in my child. Go to the third one. This is 629, and that is 606. This is definitely better. So I take a copy and put it here. So like that, we keep taking one from each parent and construct my child, taking the best things from each parent and construct my child. Now, when I do, that's a perfect recombination, right? No other algorithms have this kind of facility to create a child. Now, once I do that, I had a requirement of 3 here and 2 here, but you see, I screw it up, right? Because I'm taking something from here, something from there. So it's not matching what my demand is. So I use mutation operator, first one, to fix that. And it's like a puzzle that I need to take one of these out from here to make it 2. And I look at which one I have already accessed. So I'm going to take this one out, okay, and make this 2. And I could do that process in a very, very simple order n square each time and make sure that my these demands are all met. Then mutation 2 comes and says, can I fix this kind of constraints, which is more than 650? Some cases I can, and some cases I cannot, but I leave it if I cannot. So it's, again, arranging some of these numbers so that this one reduces below its limit. So that requires order NH. So these two mutation are basically repair operators trying to give me what the reproduction has produced to a more feasible like solution. So if I go back to 310 variable problem, you see I can get the same accuracy solution with my algorithm in 0.04 seconds, 1000 variable, same accuracy solution in 0.05 seconds, 2000 variable that the Cplex could not solve. Now I can get 99.596% with just in 0.19 second. So that's really small size problem. Remember, we have to go to 50,000 variables. So here is the big picture. 50,000 to 100,000 is what the company needed. And here is the computational time to get to a solution which will be 99.7% utilization. So none of these solutions I am guaranteeing to be optima, but they're very, very close to the optima, because optima will be somewhere from 99.7 to 100%, right? You cannot have more than 100% utilization. So it takes about 10 seconds to 50 seconds to solve the problem. But out of academic interest, I now increase the number of orders and all that we have so that I construct a billion variable problem, okay? And my algorithm scales. So this is a log-log plot, and you see I get a straight line. If you ever get a straight line in a log-log plot, means you have a polynomial time performance. So I've come up with a polynomial time algorithm now in a large range of variables to solve this problem with 99.7%. But you might ask me, how about the optimum? How much time do you need from going from here to the optimum? By the way, this problem is one of the largest. I have not yet seen any other optimization problem that has been solved with a billion variable. It's a huge billion dimensional search space where we are looking at. To answer that question I just asked, what we do is we increase our requirement that we want to converge with 95%, 97%, 99% like that. So 99.7% is what I showed you. You see that here now, it's a log-log plot and I get an exponential. So actually you have a super exponential algorithm here. That means if you want to get arbitrarily close to the optima, you need exponentially more time. So many people unnecessary attempts to get the optima, but if you're happy with an approximate solution, which can be close to the optima, you can get a very fast algorithm like polynomial time. But if you really want the optima, that's where you have to spend that exponential time. So if you don't need it, don't unnecessarily put that extra time. Okay, now coming to the multi-critical criteria optimization, you basically have more than one criteria. So you want to minimize cost. So this kind of solutions may look good, but then if you are thinking of another kind of criteria which is in conflict with the cost, like comfort, safety, longevity, all that stuff, this kind of solutions, which is very cheap, may not fare well. If you say, okay, what is the best solution for that? You may have something like this, which may cost you 10 times more in some currency, right? So if you think of all possible cars that anybody can produce, let's say hypothetically that can fall anywhere here, but any solution you give me here like this one, I can immediately give you a solution B, for example, which has a better cost than that, you see, smaller cost, and also has a better comfort because it has a higher comfort than this. So B, A, and C seems to be having better values for both objectives than any of these blue point solutions over here. So in that sense, all the solutions that are falling on this red line are called optimal. In the context of multiple criteria optimization, we call them as Pareto optimal solutions, simply because the scientist Pareto from Italy had first proposed this idea way back in 1896. So in multi-objective optimization, the bottom line is that you have number of solutions that are optimum. So your goal would be to get a good representative set of all the optimal solutions, the whole range of solutions. And then you have to finally pick one based on sitting with the decision makers, using their preference information and picking one. But getting a set of solutions has a lot of advantages, as I will show you. So that's the whole concept, but there is a mathematical idea that comes with the partial ordering concept. In multi-criteria optimization, we call them domination principles. So now you have an objective space, like you have a F1, F2 space. Before with single objective, you just had a real line, but now you have a space here. So any point here, if you're minimizing both objectives, will be better than all the points that is in the green region, but any of the points in the blue region is better than this point X here. So when you keep doing so, you have a push towards getting this way when you're minimizing both. And eventually there will be a border of this objective space where you will get stuck. And that's your optimal, one of the Pareto optimal solutions. But actually you get a number of Pareto optimal solutions like that. So classically solving these kinds of problems is that you combine multiple objectives to a single objective, either by a weighted sum or there are many other ways. And then you solve this single objective problem like the methods I talked about so far, and you get a solution which is guaranteed to be one of the Pareto optimal solutions. If you want to get another one, then all you have to do is change the weight vector, because where you get with a particular weight as a geometric relationship, because the slope at the Pareto front, like the slope here I'm showing here, that is the ratio between the two weights. So if you change the weights, your ratio changes and your tangent changes, and you will converge to another point. So if you want to get a set of points, just to have a representative set of points to have an idea of the entire Pareto set, you have to do multiple runs with changing weights. But if you have a problem like this, some problems have this non-convex Pareto set, then in this non-convex area, you will not be able to find any point using this method. But there are some fix-ups, like you go to epsilon constraint, where you put an artificial constraint or more than one artificial constraint, restricting other objectives to be less than certain value and minimize F2 for this. In this example, you can minimize F2 subject to F1 less than epsilon 1. So this becomes your feasible space now, not the entire thing. And when you minimize F2, this is the point you get, which was difficult to find using the weighted sum approach that I talked before. I think the problem with these methods is that multi-objective optimization is treated as an application case for single objective optimization. So that's kind of anti-computing concept. Usually you should have a generic algorithm for solving multi-objective problems. Then if you're solving single objective, your algorithm should degenerate. But then then optimization algorithm, it's literature is just the opposite. So that's the issue that I had when I started looking into it and thought of these population-based methods where we start with the problem. We don't ask for weights or epsilons or anything. We just find a representative set given the problem and then go to the decision maker and say, these are some very good alternate solutions we have found. Now choose one from it. So this is a much better kind of way to choose a solution and solve this problem rather than, first deciding what to find and then go and find it, right? And there is a book I wrote in 2001. If you're interested, you get more information about the motivation of this kind of work. I'm going to show you one algorithm and how it works. Use a population-based methods that we proposed way back in 2002. This is a well-celebrated algorithm. Actually, it appeared in IEEE transactions. There is currently about 50,000 Google Scholar citation on this one single paper. It's called NSGA2. So what it does is for 2 and 3 objective problem, it starts from the search from within your objective space. And then with iterations, it comes towards that patch of the boundary, which corresponds to the Pareto set. And it gives you a good representative set of that. So I'm going to show you with an example. 1 second. Yeah. Let me leave the algorithm here out, but show you some simulation of that. So here is in a 2 objective problem, F1, F2. The line is the Pareto set because there's nothing below it. You see this algorithm starts from a random place and how it with iteration comes and converges to the front. And then if you keep running, the distributions get better and better. Here is the one with 3 objective problems with F1, F2, and F3. And you can see how nice a Pareto surface you can get eventually, starting from a random set of points. Eventually, with iterations, they go towards the Pareto set and gives us a good idea of where is the Pareto set, because there is nothing below this surface, okay? So this, the literature in this started around, as I said, early 90s, and you can see there have been an exponential growth. But around 2010, this was kind of stabilizing. Okay, and that happens to many fields because there's a saturation level of every field. But then something happened around this time, I would say, that it's again another exponential growth has started. And I believe this is what is known as the many objective algorithms that we have been developing since around 2010. And this means that all these methods like NSGA2 that I mentioned can solve 2 and 3 objective problem nicely, but they don't work very well when you go to 5, 10 objectives. Now we have algorithms where we can go up to 20 objectives. So these methods are getting now very, very popular. So if you think of where these kinds of algorithms are being used, about 50% of them are in engineering and computer science, but another 50% with a large share in mathematics. But you can see physics and astronomy, decision sciences, environmental science, social science, even medicine. So this is an idea that got developed from computer science and engineering and went all the way to various different fields because people in these different fields need this kind of multi-criterion method. So it's getting very, very popular now. There are a couple of examples I'm going to show you. One is this, which is from an auto industry here near Detroit. Their goal was to design the engine for 6 objectives, 6 criteria. One of them was the weight. So they have a current design that was weighing 184 kilo, but they wanted to reduce it by 10 kilos. That was their goal, but also optimize other 5 objectives. So I asked my student first to figure out how difficult it is to find a feasible solution. That means how constrained the search space is. There are 145 design variables, 146 constraints. So he ran this black box code that they had given us for evaluating a solution over the weekend, I think over the few days as well after the weekend, for 2.5 million variable solutions. None of them was turned out to be feasible. So you randomly create 2.5 million solution, none of them is feasible. So then we realized that we were dealing here with a very constrained, highly constrained search space. So our algorithm had to take care of that aspect. Eventually, we modify what is known as NSGA3, the many objective version of NSGA2, and then find these solutions. And I'm showing you this plot. This is called parallel coordinate plot. So these are each of these 6 objectives. Ignore the last one. This is some kind of a difference between the solutions we are plotting to show that we found different solutions. This is the weight. You see that the worst weight we got was 174, and they needed that. And the best we got was 167. So there are about 100 solutions here. So not only we gave them 1 solution below 174, we give them 100 solutions, one having about 167, so about 14 kilos less than what they were looking for. And then we find lots of differences in the solutions because there are other objectives that come in. So if you follow one solution, this is the weight, then this becomes your second objective, this becomes your third objective, and so on and so forth. But if you compare with another one, like this best one, it has a different way of doing it. So each of them is an optimal solution with a trade-off. If it is better in weight, it may be worse in something else compared to another solution. So our algorithms can find many of these such solutions. Okay, now going to some of the recent methods, research where this is going on very quickly. Of course, we are doing the algorithmic development. This is continuing. We have public domain software in Python called PyMu, Platimo. PyMu is our distribution. You can find lots of algorithms coded there. These methods, because you're dealing with a set of points, you need to compare sets. And there are some methodologies that are there like hypervolume, IGD metric, and different things. Visualization becomes an important thing. How do you visualize more than 3 dimensions, right? So there is a lot of challenge here. People have been proposing a lot of different ideas, taking from the data analytics literature. Then there's a question of decision-making that I mentioned. EMO can find a set of solutions. You cannot leave it there. You need to also finish up with the decision-making. So we are having algorithms where it combines EMO with decision-making. There are some methodologies we have been proposing, and that becomes, these are some new research ideas that people are working on as well. Sometimes you are not interested in the entire Pareto set, but only a part of it. So how can I concentrate on a part rather than the entire set? And the part can be dictated by some reference point or by some other way. So dynamic, where the problem is changing with time. So your Pareto front changes with time, and how do you go and track it? Hierarchical problem, combinatorial problem. Parallel computers. So if you have parallel computers, you may find a part of the Pareto front by one processor, another part by another processor, and then third processor can find another part. So you can distribute the load of working and finding the Pareto set among different processors and eventually collect them and say that this is my entire Pareto front. There are various things we're doing here, surrogate modeling, where the objective functions can be very expensive. So you make a surrogate model for optimization, and that kind of methodologies are going well as well. Uncertainty-based optimization, where we get into robust and reliability-based design solutions, where your solution that you ultimately recommend need not be very, very sensitive. So you change your solution slightly, and you get a huge change in the objective function. You don't want that. So you may end up with a robust front that may look like this. So instead of finding the optimal set, you go and find the robust set. So all these different practicalities that we've been working on. I want to just finish up with one concept and then one big societal example. So the innovization concept introduces the machine learning ideas into the optimization. When you find this Pareto set, there are a number of solutions. You can now look at these solutions and see if there is any common hidden principles that are kind of shared between all these solutions. So you can apply a data mining software or an algorithm to find out what is common in them. When we do that, we find really interesting properties of solution or knowledge for the solution. This is a gearbox design problem where all variables being constant except one that varies this entire Pareto set. And you see that's the module, which is some property of the gear tooth geometry that varies with one of the objectives in a square root manner. So this is a module proportional to square root of power. It comes out as a thumb rule, which is the property of all optimal solutions. So not only you find these optimal solutions, but also you find some property that is stored in them, and that stays as a knowledge. One of my students, while I was teaching this at IIT Kanpur, took this as a term project where he tried to create cricket teams for 2020. So every dot is an 11-player team. And then he actually tried to minimize the bowling score and maximize the batting average. He ends up with these 100 different teams. And this was done in 2020. And Chennai Super Kings actually was the champion that year. So what we are showing here is we could find few of these teams that are better than the Chennai Super King in terms of both bowling and batting. So that says that our solutions will be pretty good. Now, what I'm showing you here is every team has 11 players. If I collect all of those players and see how frequently they are appearing here, you can see some of these names, which are that year, I mean, almost you're talking about 13 years ago. They were very, very popular, right? Saha and McDonald and others. So there were 129 players he considered, but only 29 of them come in these Pareto teams. So if I am the team owner, maybe I should do such a study, figure out who are the key players, both in terms of both aspects of the game, and then I may go and choose these players. And this can be done in various other team choice problems as well. Let me skip this slide and get to the last example, where we did this to a New Zealand farm, where it's a farm area. This is a sketch, of course, which is owned by a local tribe called Maori there. They think almost they can do anything to their land. So they can use any kind of fertilizers to grow grasses so that they can have more milk, meat, and everything. But they don't realize that some of those fertilizers, toxic fertilizers, are actually getting washed by the rainwater and goes to a nearby lake, which is not their property. Okay, so government has been always telling them, you can't do this, you can't do that. So when we went there and tried to solve the problem, these two groups, the Maoris and the government, will not talk to each other. But fortunately, the forest department was giving us all the data, the models of how the water flows and the landscape information and every possible information that we needed. So we call this method wisdom. It actually, our application won the Wiley Practice Prize in 2013. So here is the landscape exact area. There are 315 paddocks, as they call it, where they can go and change any land use in next 10 years. There are 100 different options you have in each place, and you have 10 years to do this. So I quickly calculated there are so many different solutions that exist. That's a very small drop. You can see that compared to the number of atoms in the universe. So it's a huge search space we are talking about, astronomically large search space. So you need to deal with such problems when you're dealing with real world problems. Our goal is to change some of these so that 14 different objectives gets optimized. Some of them are related to environment, some of them are related to their productivity and profitability. So we developed a virtual reality-based system so that these local Maoris, leaders who are usually not very educated, can get an idea of the solutions by looking at these plots. They are life-size plots. So here I'm showing you how in the environment-friendly solution changes in 10 years from what was given to us. In the end of 10 years, you get one of these solutions that is shown at the end. So I show them the evolution of how we are getting in the 10 years. And then if I take the environment-friendly solution, which I've shown you, and the highly profitable solutions, 2 from the 100 solutions that we found, we now do the decision-making because we've got 100 solutions. How do we pick one? So we first go to the Maoris and start with this highly profitable solution, okay? So they obviously don't like it because, we start with the environment-friendly solution. For the Maoris, they don't like it because it doesn't give them enough profit. It's good for environment, good for government, but not for the Maoris. So we come this way, okay? And at some point they say, okay, we can live with that. Then we go to the government because they are not sitting together, right? So we have to do this independently. We go the other way, and then we find a bound where they were happy. Fortunately, there are 4 solutions that were kind of in the intersection of the two, and they could not decide on one of those 4. So we then take this another process called analytical hierarchy process, where the stakeholders are still used. You see, there are some Maoris, there are some local government officials. Each interview took about 2 hours. And then we follow this procedure with their input and come up with one solution. So in this parallel coordinate plot with 14 objectives, you can see this, all the green solutions are what we have found. There are 100 solutions there. These 4 solutions is what they picked eventually, but they could not converge to one. But when we did this process of analytical hierarchy process, we found the winner, which is the 3rd one. You can see it's slightly different from the other. So this process also, they were apart. So I believe this can be a way that you start with the astronomically large search space, do an optimization to find about 100, 200 solutions, then sit with these decision makers to narrow down the choice. If you can find one compromise solution, great. If not, end up with the AHP. So this can stay as a way to solve societal and large-scale industrial problems of multiple objects. Since then, we have taken that and solved some problems from Finland, for example, the forest management problem, where there are different kinds of species of trees. You want to keep a diversity of them. You don't want to cut all of them. So how do you cut? Which trees do you have to cut at what time? So that's the schedule we give them. So there are 3 objectives we consider, which end up with the Pareto surface and all that. Recently, we are working with another climate change issue here. Is the Chesapeake Bay watershed in the east coast of US. It's a huge area. They are interested in minimizing the nitrogen loading onto the atmosphere, as well as the cost of doing that. And we are finding this trade-off frontier where one of the environmental protection agency people can go and click a point and see, this is the West Virginia, and they can see what kind of BMPs, what kind of treatment we need to do there. That will cost us so much, that will reduce so much of nitrogen. If they don't like this much reduction of nitrogen, they can go over there and find another solution which will make them a bit more costly, but then they can reduce more nitrogen. So that's the kind of thing we are going into. This work also got the best paper award. So some of these are have a lot of potential and nice ways of solving these practical problems. So what I try to show you today is that practical problems require optimization, different kinds of problem. Classical methods help you get the foundation. Evolutionary methods are practical ways of really getting there because these methods are flexible. You can change them. If you have parallel computers, you can use them. Evolutionary multi-objective methods find multiple solutions in a single run, as you've seen in the simulations. Customization is the key. So you can actually customize your algorithm to make them faster. I think finding multiple solutions and then analyzing them to get more knowledge and all that are becoming very, very interesting. And they have tremendous potential in lots of different kinds of problem solving. So with that, I'm going to stop and take some questions. If you have, here's my email address and my lab web address. Thank you for listening.
Thank you very much, Professor Deb, for enlightening all of us, including there are some students, some research scholars, and the faculty members who are there in the list of attendees. Well, there are certain questions which have been shared. So what I'll do is I'll just share my screen.
All right.
And I hope all of you are able to see the questions. Is it so?
Yes, yes,
Okay.
I'm seeing that.
Yeah.
So first question is, what is the weight vector? So weight vector is how you weigh different objectives. If I have 2 objectives, let's say minimize cost and minimize the environmental effect. So I want to say, I want to give 60% importance to cost and 40% importance to environmental effect. So it is 0.6 and 0.4. That's the weight vector. But you see, that is my idea of 60-40. Your idea could be 70-30, giving more importance to weight, or maybe more importance to environment. It could be 30-70, right? So that's the weight vector. But because your final solution will depend on the weight vector you've chosen, you never get this entire Pareto set. So in order to get the Pareto set, you have to run it again and again with different weight vectors. When I talked about the Detroit-based company, Detroit is a city here, which has all these auto companies like General Motors, Ford Motor Company, and all that, Chrysler. So I'm actually close to Detroit here, about a 1-hour drive from here. So we get quite a few projects from them because auto industry have lots of ways to optimize. So in that context, I was mentioning Detroit. Is it correct that the ultimate goal of multi-object optimization is to help a decision maker identify solutions of interest? Yeah, achieving satisfactory. Exactly. Yes. So, as you'll probably agree with me that any of these problems that we are trying to solve today from industry or even academics, you cannot put one criteria and say, okay, I'm only interested in the weight of these object, this component, this engine, for example. Immediately other things comes up that how about the performance? How about the quality? I also want to maximize them, right? So that's what we're talking about here. Our goal is to maximize more than one criteria simultaneously. As it turns out, if there is a conflict in these objectives, there is no one single solution. So it ends up with a number of Pareto solutions. So now, instead of finding one best for the weight and best for the performance, we try to find a representative set of Pareto solutions. And then the decision makers have to come in, because to an optimization person, any of these is an optimal. Okay, any of them can be chosen in practice. Okay, but the decision maker have to choose one for the particular year, or maybe for the particular time and the availability of money and everything that they have. Their company's motto, are they more into producing cheaper cars, or are they really known for producing quality cars? So their solutions may depend on that. But the idea, they will choose one from it. But the idea that all the Pareto solutions give them is the whole range of solutions that are possible, or alternative solutions that are possible. Now, in some situations, companies can say, oh, I am always interested in 80% importance to cost and 20% importance to environment. If they are so sure, then they can go ahead and make one weighted sum and solve it. But I can guarantee you, I have not seen any company who's telling me so positively or so surely they know that. So because there is a kind of uncertainty there, it's better to go in this mode that I'm talking about first. Find a set of solutions and then do the decision making. Okay, third question is, in efficient evolutionary algorithm inspired by shift-based density estimation, can one propose population maintenance method to high? Yeah, so you're basically talking about some details about how an evolutionary algorithm can be developed. So there are concepts of density, and then wherever there are more dense solutions, you can shift your algorithm, or finding more children to those places. Any of those things are going to be useful. But we often notice that the Pareto set does not have a uniform density of solutions. Certain part of the Pareto forms have more solutions. Certain parts have little less solutions. This is particularly true if you have a discrete search space. So your algorithm, so now it depends on your goal, right? If you're saying, no, I still want a uniformly distributed set of points, then you ignore the density-based optimization. You just go and find a uniform distribution. But if you say, no, I want to really have, if there are more solutions in one part, my representative set should also have more points on that part, then maybe what you are proposing would be a very good idea. So it's a detail in the algorithm, and it may be good to have some such population maintenance algorithms that uses, where the more dense solutions are, because naturally our algorithm can go there, but you still want to find some part of the Pareto set where there is less dense solutions to give the decision maker an idea of all possible combinations or different alternative combinations that are possible. So I agree with you. Yeah, one can propose such a thing. Then the fourth question is, an effective multi-objective algorithm can achieve a set of optimal solutions that can make a trade-off between different objectives, correct? What is the difference between this multi-objective algorithm and multi-objective differential? Oh, okay. Based on decomposition. So this multi-objective concept I told you about, the optimal solutions, there is a multiple optimal solutions that it gets into. That's the concept. Now you're talking about different algorithms of finding the representative set. I showed you genetic algorithm based. I haven't showed you the differential evolution based, but there are mode methods like multi-objective differential evolution algorithms that are already existing. They're quite popular as well. So they exist, yeah. So those methods are comparable as well. Now the difficulty comes when you go to more than 3 objectives. So now you have, let's say, if you have a 5 objective problem, you're dealing with a 5-dimensional Pareto set. You can't visualize it, but you can use an algorithmic means by which to get there. So differential evolution methods are proposed for that as well. But all the papers that are coming out recently, I'm not seeing any comparison with mode methods, like differential evolution being a contender when you have large dimensional problems. So they were very good in 2 and 3 objective problems, but somebody needs to look into that differential evolution literature and see if they can be converted to better multi-objective, or we call them many objective now these days, many to say more than 3. So many objective differential evolution algorithm. So please look at that and see if you can propose one. I think we need some such method. So then you will become quite famous if you can come up with a very good competitive method using differential evolution. There are, by the way, other evolutionary methods are also used for multi-objective, like PSO, particle swarm optimization. There is MOPSO. And then many other meta-heuristics methods have been also converted to solve multi-objective problems. Hope that answers your questions.
Yes, I suppose I just invite the attendees, if there are any more questions, you can type out in the chat section. No, I don't think so. There are any more questions. Well, thank you very much, Professor Dave, for such a lightning talk and sparing your valuable time. I must appreciate your commitment towards delivering this particular talk. It's an evening around 8 o'clock here, and I think it must be early morning at your place.
No, it's about 9:30 now here. So
Okay, okay.
yeah,
So on
it's very
behalf of
good.
the host institution, that is the Deen Upadhyay College, University of Delhi, and the National Academy of Sciences India Delhi chapter, I would like to thank you once again, and to all the speakers and to all the attendees who have been there with us all throughout the workshop, and hope that the attendees will join us again for another interesting talk which is going to come up next week. Thank you very much.
Thank
Okay.
you. Thanks to everyone for
Thank you.
listening.
Thank you very
And
much.
thank you for
Okay.
organizing it.
Bye bye.
Okay, bye-bye.